Hello everyone. In this session, we're going to talk about fully developed turbulent flow. In previous session, we already talked about the characteristics of laminar flow in pipes and fully developed laminar flow. So we want to know the similar things for turbulent flow, right? So here, let's talk about turbulent flow. So we say when viscous flow, when viscous effects are present, the flow can be either laminar or transition in the transition period or turbulent, depending on the Reynolds number. For example, in a circular pipe, in the pipe flow, Reynolds number under 2100 is laminar and over 4000 is turbulent. And in between 2100 to 4000, it is a transition period. And from this graph, 8.11, we can see that at the beginning, in this graph, it shows you time versus the axial velocity, axial component of the velocity in the pipe. And we see at the beginning, the axial velocity increase with time if we increase the volume flow rate, for example. And at the same time, Reynolds number will increase. So the laminar flow started as laminar, and with the increasing Reynolds number, it turned to be towards transitional period and turbulent. And when we are in the turbulent zone, we can see that if we look at the axial velocity, it does not change much when we fully increase this velocity, axial velocity. And when we look at this axial velocity, we can see that the characteristic of turbulent flow is in that the chaos of this flow, right? So comparing to the smooth increasing velocity here, we can tell the center line velocity or any, we can follow any particles just to track the axial velocity. But in turbulent flow, it's really hard to do that. And you can see all this zig in your turbulence. There is a mean velocity going on, but you see the turbulence give us more chaos in the velocity profile. And as we said, we want to do the same thing for turbulence flow, which means we want to understand this fluctuation, how to characterize it, how to understand this volume flow rate, how to understand viscous effects, viscosity, shear stress, pressure drop, and so on for this highly turbulent zone, highly turbulent fluctuations. So if you were given this velocity profile, which is axial velocity versus time, and if we look at figure 8.12, let's say here, and you can see velocity change with time like this, right? So how would you characterize it? You might think a good idea is to do the same thing, right? We take time average to get a mean value, and the difference between any single point with a mean value, we call it the fluctuation, right? So we have the time average term U prime and a fluctuation term and time average term U bar and a fluctuation term U prime. This is a good description of a parameter of turbulent flow, right? So we have a very similar term with laminar flow, which is U bar here, and another fluctuation term, which is U prime. All right, here, before we talk about more on how to examine this flow, let's take a look at several examples here to see what is the difference between laminar flow and turbulent flow in real life. For example, this is paint, right? If we want to mix the paint with some color, for example, red color, and we can disturb it this way, right? But you see, it is really hard to mix this paint, mix this color into the paint, right? Although we disturb it, and you can see with this low flow rate, for sure the flow is laminar flow, right? But if we disturb it this way, we can see, well, with the low flow rate, the color is really hard to mix into the paint, right? You see some red, and you can still see the straight lines of the color red, which is not fully mixed, right? This is laminar flow. And let's take a look of another example here I want to show you. You all have the experience of sometimes when you want to mix cream into your coffee, what will happen, right? So this is a video showing you, all right, so I dump in this cream into a cup of coffee. This is what happens. The cream stays at the bottom, right? Settle down at the bottom of the cup. So we want to disturb it to mix. And you see, if we disturb it, mix it with a spoon like this, and stir it at very low velocity, you can see the mixing happens very well, right? With even a low disturbing rate. And if I mix it, if I disturb it, or say stir it even faster, right? You can see all the vortices going on, and that is definitely turbulent flow. And with turbulent, we can mix this cream with coffee much better than the previous case, right? When we want to mix the red into the paint with a low Reynolds number and the laminar flow, that was really hard to do. So if we compare these two cases, one is laminar diffusion, another one is turbulent diffusion, and we do this experiment comparing them in a graph. This is what's happening. And you see, in laminar flow, in diffusion happens, but it's very slow and happening at a very slow rate, right? But if you look at turbulent diffusion, all right, so with all these vortices and disturbances inside the flow, the velocity change a lot with the fluctuation. Diffusion happens much faster, right? If you compare the green are merged into the whole area much faster, right? And comparing to that, you see the laminar diffusion happening very slow, very, very slow here. By looking at these videos, it should give us a good idea of how we want to treat turbulent flow, to examine the characteristics of turbulent flow. So similar to laminar flow, we have mean velocity, right? We have a mean velocity, and the fluctuation is it's all happening about the mean velocity. And we also have a fluctuation term. We say the fluctuation is if we do deduction of any single fluctuation point, any velocity point, axial velocity here we're talking about. The difference between that velocity, that real velocity, with the mean velocity give us this fluctuation term, which is always non-zero here, right? But if we do a time average, all right, single u prime is not zero, but if we do a time average, it might be approaching to a number which is approaching zero, right? It's if you do the fluctuation in average, and you will see some are positive, some are negative, right? The average might be towards zero. And then if we look at this u prime squared, since u prime is now zero, right? U prime is now zero, then u prime squared might not be zero either, right? And also u prime squared, since you are taking square calculation, it should be either zero or positive. So this way we exaggerate the flow fluctuation by taking the square of this fluctuation, right? So this way we can calculate, after exaggeration, comparing to the mean velocity, what is the intensity of a turbulent flow. So we define this density, turbulent intensity when we have a large turbulent intensity here, we know the larger fluctuation of the velocity is. Also, using this idea, we can examine things like flow shear stress and so on. For example, if we compare laminar flow shear stress and turbulent flow shear stress, we see laminar flow shear stress are caused mainly by random motion of molecules. And turbulent flow, it is a 3D, three-dimensional fields and all random happening, and it's the 3D eddies that cause this shear stress. And quantitatively, we can write shear stress in a different way, which the first term, u mu du dy, here u, we're using the mean velocity. This term we call it laminar component of the shear stress. And this second term, minus u rho times u prime v prime bar, this is the average of the fluctuation of velocity in the axial component and the y component, right? In the vertical direction component. And this is the turbulent component. If u prime v prime is 0 for laminar flow, we know u prime v prime bar is 0 as well. But for most of the cases, for turbulent flow, u prime and v prime are not at the same time to be 0. So, and also u prime and v prime are usually give us a negative number. So this minus rho u prime v prime bar will give us a positive number for turbulent flow. So this way, we can examine the turbulent shear stress by combining the laminar shear stress and the turbulent shear stress together, by combining the mean velocity effect with this fluctuation effect. Here, figure 8.15 shows us the structure of turbulent flow in the pipe for shear stress for part A. For example, if we look at this graph A, it is shear stress in the R direction along the radial direction versus R, the location in the radial direction. And we see any single point we pick, all right, the shear stress has two components. It has a laminar component and it has a turbulent component. And this is the pipe center line. This is the shear stress, right? This is the shear stress. And we say in a flow, we want to consider shear stress, and the flow is driven by say pressure drop, right? Pressure difference. The shear stress might be at the center line, should be balancing this pressure drop. It is linear, right? So if we look at any single point, we say there is a laminar component and a turbulent component. But if we look at a place or a location near the center line and look at a location, say very close to the pipe wall, the component, the shear of the component is quite different. For example, if we look at this point, all right, this point, which is near the pipe line, near the pipe center line, we can see that the laminar component is much smaller than the turbulent component, right? The shear is much smaller in the shear here, I mean the portion of the laminar flow, of laminar shear stress is much smaller than the turbulence. And if we look at a point here, for example, then the laminar component, all right, is this much, and turbulent is this much. Turbulent effect is much smaller than laminar shear stress, which is laminar. When we talk about laminar, and we say laminar flow is related to something like viscous effect, right? The no-slip condition. So when we are towards the wall, the shear effect is actually much heavier, right? And towards the center of the pipe, it is the turbulence dominates the flow. And we can also see the same trend if we look at radial velocity, the axial velocity change in the radial direction, which is u bar in the r direction. And we can see that the axial velocity change in the r direction, changing the radial direction this way. And we can break down this whole area, all right, this whole area into 3 zones by looking at its shear and a velocity component. The first zone we call it viscous sublayer, right? Viscous sublayer is where the viscosity effect is the heaviest. And the outer layer is where the turbulence dominates, and in between we call it overlap layer. So by looking at velocity and shear stress, we can break down this whole flow area in the radial direction into a viscous zone, an outer layer zone, which is dominated by the turbulent flow, and between these two, there is also a transition we call the overlap region or overlap layer. And you can see that velocity change in the viscous layer much faster than when we are towards the center line, right? So because of the shear stress or the viscosity effect, you can see the gradient here are much higher, and towards the center line, the velocity doesn't change that much, right? So the gradient is that much higher at the beginning for viscous layers, and towards the turbulent layer or outer layer, is the velocity doesn't change that much. It is very close to the center line velocity when we pass the half of the area, right? And we mentioned that turbulent flow is an area which is the least studied or most studied but least understood in fluid mechanics. It is still very hot topic, although many researchers have been working on this topic for many years. Still a lot unknown about this field. So when we talk about turbulent flow, usually many methodologies are used. Dimensional analysis is one of them because of the complexity of this problem. Many variables are involved, right? So to reduce the problem, reduce the complexity, reduce the number of variables here, dimensional analysis is very useful. And with dimensional analysis, we also can know some dimensionless variables, dimensionless parameters that tells us the essential problem, right? What is the essential of the problem? Here, if we do dimensional analysis, this is what we get for the structure, typical structure of velocity, turbulent velocity profile in the pipe. And let's take a look. As we said, the velocity component can break down. Well, if we look at the axial velocity, the velocity field, velocity profile can be broken down into 3 layers. The layer very close to the pipe wall is called a viscous sublayer, and the layer that is far away from the pipe wall, which is close to the center line, is turbulent layer. And in between, it is the viscous and the turbulent effect, both acts, right? Both dominant. No one wins. And this layer, we call it a transition layer. And in the viscous layer, the equation, dominating equation is this, and u bar over u prime, u star equals to y u star over mu. And in the viscous sublayer, we say that it is approximated to be a linear relationship. And at the outer layer, the turbulence effect, we use this equation, all right? These are all empirical studies, and all the parameters are decided by the empirical studies. But here, we introduce something called friction velocity. Right? U star here is a friction velocity. If you want to see how it is defined by the shear stress at the wall over the density, and take square root of it, and by physical meaning, you can tell it is not actually velocity, but it has the same unit of velocity, right? And here we don't have time to talk about examples, but in class I'll show you a bunch of examples to see how we can use this information to tackle some real problems. And since turbulent flow is a very important but difficult topic, the analytical solutions, like if we just apply control volume analysis or differential analysis, one very single methodology will not solve the problem, and analytical solutions does not exist. So turbulent modeling is a good tool to help us to understand more about this topic. And with this shear stress term, Reynolds shear term, and mean velocity, the Navier-Stokes equation in here, which is the main equation usually we solve in fluid mechanics, right? Turns to be having lots of more terms in the momentum equation, which is really a hard topic. And as the textbook mentioned here, although considerable progress has been made, but still a lot has to be done in this area. Alright, so this concludes fully developed flow for two cases, laminar flow and turbulent flow. And before this, we also talk about before fully developed flow happens, what do we have? We have the entrance region, right? We talk about for laminar flow, for turbulent flow, how do we calculate entrance region, how do we calculate variables like pressure drop, shear stress, velocity, mean velocity, centerline velocity, and so on for fully developed turbulent and laminar flow. So this concludes our calculation, the main calculation for pipe flow. And one more thing we want to talk about. So when we talk about laminar flow, turbulent flow, here we are focusing on Navier-Stokes equation, now the terms in Navier-Stokes equation, which is pressure, forces, shear stress, velocity, and so on. So we haven't touched anything about the energy head or the energy related to terms in flow yet. So let's talk about Bernoulli again and talk about what are the energy terms, how the energy terms involved in the pipe flow. Alright, so in section 8.4, let's talk about head loss in pipe flow. So before we talk about head loss, in Bernoulli equation, if we follow Bernoulli equation and we make all these four assumptions satisfied, we find that in Bernoulli equation, total head for a single point, if we along the streamline, we follow a streamline, total head for one point should be equal to the total head at another point if we follow streamline, right? So this is happening when we don't have shear stress, when we have incompressible flow, right? Steady state. And what else do we have? We follow a streamline, right? So when we have laminar flow, we have streamline. When we follow streamline, and we have the total head from one point equals to another. In real world, this is usually not the case, right? We don't have total head from one point to another. When we do the EFD NetLab Venturi test, we all experience some total head loss from the beginning, beginning the inlet of the pipe to middle point, right? If we take a look of point A versus point E in your experiment in Venturi test, we all experience some total head loss, right? So in this section, we want to talk about where does this total head loss come from? There are different components that contribute to this head loss. We say for sure yes. And let's talk about what are they. Just by looking at these four assumptions in Bernoulli, we can give a good guess, right? The head loss might come from when we have shear stress. Head loss might come from if we don't have laminar flow. Head loss might come from if we don't have steady state flow, or from if I have a flow that has to count in the compressibility of the fluid. And in pipe flow, usually pipes are connected by something like elbows, and in real life applications, you will have valves and other equipment connected to your pipes, right? So here we can summarize and break down our head loss into these two big groups. One is we call it major loss, and one is we call it minor loss. And major loss are due to shear stress, or let's say more broad, we can say it's due to viscous effect. All right, and what about minor losses? And minor losses are due to, say, various pipe components, such as if you have a valve or if you have an elbow or something else, right? So for major losses, we find that the major losses and the major total head loss for a pipe flow can be, from dimensional analysis, we can find that major loss equals to something called friction. F here is friction times L over D, which is a dimensionless term here, times V squared over 2G. And we already talked about for laminar flow, this friction factor equals to 64 over Reynolds number, which is when we have increasing Reynolds number, this friction factor decrease, right? So please read this chapter, section 8.4, rest of section 8.4, to see how do we treat this friction factor for turbulent flow. All right, so please read this section and summarize your findings for turbulent flow, major losses, and minor losses, and summarize them, and let's talk about more examples and tackle some problem with this information in class. All right, thank you for watching.